It's a great pleasure to have Matthias Gaberdiel presenting today's seminar. He's speaking to us from Zurich, DTH in Zurich, and he's going to tell us about an exact AdS CFT duality, which would be. Thank you, Matthias. I will hand over to you, and we can take questions during the seminar. We're relatively informal.
Please do. Yeah. Well, so thanks very much for giving me the opportunity to present my work in this forum. I mean, I'm not quite a Diaz, but I'm sort of Diaz. I have visited before on 2 occasions, so I know the place a little bit. So what I want to describe is work I've been doing together with Rajesh Gopaguma. That's a very long-standing collaboration, been going on for more than 10 years. And then very much more recently, together with my former PhD student, Lawrence Eberhardt, who finished last autumn and is now a postdoc at the Institute in Princeton. So let me, given the diverse background, I'll start very generally, and please interrupt me if I'm going too slow or if I'm going too fast. So what this whole thing is about is about the AdS CFT duality or AdS CFT correspondence, about which you probably have heard at least on a certain level. I mean, it predicts that there is an equivalence between 2 seemingly very different physical theories. One is superstring theory on, for example, AdS 5 cross S5, and the other one is, in this context, SUN super Young-Mills theory in 4 dimensions, so a conventional quantum field theory. And that's sort of interesting because that's a quantum field theory that's not too dissimilar to the quantum field theories that play a role in, say, the standard model of particle physics. Now, I don't want to give a derivation of the AdS CFT duality, but I want to review sort of the key aspects that will be important for what I want to explain to you later. And the key aspect is how the quantities on this side are related to the quantities of this side. I mean, there's clearly some non-trivial dictionary between these very different descriptions. So what's the dictionary between the quantities on the 2 sides? And the dictionary is so how are the parameters on the 2 sides are related to one another? So on the left-hand side is always the quantities as correspond to string theory in AdS 5 cross S5. So the radius R is the radius of this 5 sphere, or inversely proportional to the curvature of the AdS space. And if you measure it in terms of Planck units, this is related to n, the rank of the gauge group that appears on the SUN side. And then you have the string coupling constant being related to the Young-Mills coupling constant, and the radius in string units is related to g² Young-Mills times n, which is what's called the TÜV parameter, characterizing the effective coupling constant of the SUN gauge theory in the large n limit. So what the radius in terms of string units means is that string theory has a natural length scale. That's the typical length of a string. That's inversely proportional to the tension. If the tension of the string is very high, then the string will be very small. And if the tension is very small, then the string will be very large. The typical size of the string will be very large. And the radius of this 5 sphere in units of the typical length scale of the string is to be identified with the TÜV parameter of the SUN gauge theory, which is just this combination g² Young-Mills times n. So that's the dictionary between these 2 descriptions. And why is this interesting? This is interesting because, for example, you can look at the large n limit of the gauge theory at large TÜV coupling. So you would take this expression large and this expression large. So what this would be, this is large n gauge theory. In large n gauge theory, the theory simplifies. The Feynman diagrams just become planar diagrams. And the effective coupling constant is this TÜV parameter. And if you go look at this regime, what this means is, in terms of the AdS description, is that the radius of the space is much, much larger than the Planck size and the string length. So in particular, the string will be very, very small relative to the space in which it propagates. And you can approximate it by a point particle approximation, which means you can replace superstring theory, which is quite complicated, by supergravity. So what this suggests to you is that strongly coupled large n gauge theory has a dual description in terms of supergravity. And the supergravity is a theory where you can calculate many things. And this is interesting because it gives insight into strongly coupled gauge theories using these dual supergravity methods. And strongly coupled gauge theories are difficult to assess. So if you believe this duality, this makes you predictions for what the strongly coupled gauge theory will behave like, and you can calculate it in terms of this dual supergravity description. Now, so I said, if you believe this, and I think most people do, and there is very good evidence that at least this version of the duality is correct. However, despite some efforts, we have not yet succeeded in proving it. And therefore, I mean, this is sort of annoying on a certain level because you base your predictions about strongly coupled gauge theory on something you don't have fully under control. But it's also limiting in the sense that you don't quite know to which extent this duality generalizes. Does this just work in this context? Which ingredients are crucial for it? Which ingredients are accidental? And there have been lots of applications where people have applied these ideas to theories that are much less well-founded. I mean, where the duality is much less well-founded from some stringy arguments. And since one doesn't really know how this duality works, one doesn't really know to which extent it will generalize and how general and under which conditions it will apply. So what we set out to do, and this was really the program Rajesh and I started many years ago, was to try to make progress in this direction. And our view at the time was that we should go to lower dimensions. And in the interim, we also realized that it's useful to look at the tensionless regime. So these are two, if you wish, simplifying features. And what I want to explain to you is that if you do this if you look at the tensionless regime and you go to the lower dimensional version, one can actually get very close to proving this duality. And that's what I want to explain in the seminar. So I'll explain in turn what it means to go to the tensionless regime and to look at the lower dimensional version and why this is interesting and why this led us to what we believe to be an incarnation of the duality where while we haven't quite proven it completely, we're very close to establishing it from first principles. So what's the tensionless regime? So the tensionless regime is that you take the same relation between the parameters on the two sides that I had on an earlier slide, but now you look at a regime where the radius is still large in terms of the Planck scale. So n, the analog of the rank of the gauge group, is still large. Or in the 5-dimensional case, it would be the rank of the gauge group is still large. But now you're looking at a regime where the 't Hooft parameter, the effective coupling constant of this larger engaged theory, is small rather than large. Now, obviously, that will make life easier from the gauge theory viewpoint, because that means the perturbation theory on the gauge theory will be a good description, because lambda characterizes that are more and more complicated Feynman diagrams that you have to include at large n. And if lambda is small, that will be a corner where you can approach this gauge theory perturbatively. Now, what's the price to pay? I mean, what does this mean from the point of view of the dual string theory? Well, what it means is that the radius of the space in which the string propagates, let's say the radius of this 5-sphere, is of the same scale or small. I mean, it can't be really smaller than the typical length scale of the string, but it's of the same length scale as the string. I mean, this relation is to be taken, this is true in the supergravity limit, so we are extrapolating away from the supergravity limit. But what people believe the small 't Hooft coupling regime corresponds to is the regime where the string size is very, very large, where the string has basically the same size. The typical string size is as large as the space in which it propagates. So what does this correspond to? This corresponds to a string that's very, very floppy. That's a string that's not tightly constrained onto a point, but a string that's very, very floppy, and as such can fluctuate wildly, can explore the whole space in which it moves, and that's what people often refer to as tensionless strings. So this is the regime where the string tension goes to 0. So what's special? So obviously something special has to happen when the string tension goes to 0, because this corresponds to weakly coupled super Yang-Mills. So what's special from the string theory point of view? And what's special from the string theory point of view is that the stringy excitations of the string will become massless in this limit. So if you think of the string as really a piece of say a violin string, then the note you play, if you play violin, will depend on the tension with which the string is strung, because the vibration mode, I mean, the energy of the vibration mode depends on the tension. So if the tension is very small, this is some very floppy string. And what it means is it costs virtually no energy to excite the string, to sort of take it out of its equilibrium position and make it vibrate. And from a string theory perspective, the particles that you see in the real world should be thought of as the vibration modes of the string. So what this means is that in this limit, the vibration modes of the string become de facto massless. So in the tensionless regime, you get lots and lots of massless degrees of freedom, and they come because these degrees of freedom line up along these so-called redshift trajectories. They'll give you lots of massless fields of higher and higher spin. So that's the special feature that happens on the string theory side when you look at a weakly coupled gauge theory in this correspondence. Now, because you have lots of massless fields, every massless field will generate its own gauge symmetry. And so what you will end up with is a highly symmetric theory from the point of view of string theory, in which you have a much bigger symmetry than you would normally have for a generic string background, because you have this additional massless higher spin fields, each of which generates its own gauge symmetry. And they lead to what people sometimes call a Vasilyev higher spin theory. Vasilyev higher spin theory is a theory where you have this typically infinitely many massless higher spin fields. And this is in some sense the most symmetric phase of string theory. That's not the phase people typically look at, but it's the phase where string theory is as symmetric as it will ever get. And if you have a chance to understand this AdS CFT duality, you may believe that sitting at the point where the theory is as symmetric as it gets is a good starting point, because there you will have more control over your theory. So the more control you have, the higher you have a chance, the better you have a chance to actually prove the equivalence using, among other things, these symmetry principles. So I think this is an attractive idea, that the higher spin corner of the duality is one in which you have a chance of proving it, because you have an enormous symmetry on the string side, and it's dual to a weakly coupled gauge theory. So you have a chance that you have both sides under complete control, and thereby can maybe prove that they're really equivalent to one another. I mean, people often say that the AdS CFT duality is a strong weak duality. That's in some sense not true. I mean, you can look at a corner where the gauge theory is weakly coupled. The string theory is then very stringy, but if you can tame this symmetry, if you can get this theory under control, then you can find also an explicit description of this theory, and thereby have a chance to compare two sides where you have both sides under control, and thereby can prove that they are the same. So that's the vision in which we want to go along attacking the AdS CFT correspondence. We want to prove it at the corner where gauge theory is weakly coupled, and the dual string theory has this enormous additional symmetry that should somehow help you get the theory under control. So that's the sort of one idea for this roadmap for how to prove AdS CFT. And this higher spin duality, this has some history. So there is based on this idea that there should be this description, and there should be this tensionless string theory emerging. Klebanov and Polyakov proposed that there is a duality between a higher spin theory and AdS4 and the three-dimensional Orrin vector model. This is not directly related to string theory, but that's sort of a proposal in the spirit of this. And what started this whole endeavor was work by, in particular, Gyombi and Yin of around 10 years ago, where they gave very non-trivial evidence for the fact that this duality is in fact true. And that sort of gave an impetus to the idea that these higher spin CFT dualities may be a useful corner of the AdS CFT duality. Okay, so that's sort of the one strategy. And what's the other key ingredient? The other key ingredient is to consider the lower dimensional case, in particular string theory and AdS3. Now, I think this is something many of you are familiar with. Life in lower dimension tends to be simpler than life in higher dimensions. And therefore, you would expect that somehow you will have a better control of getting this theory, or both sides of this theory, under control if you go to lower dimensions. And again, if you want to prove it, maybe you should start with the, in some sense, simplest incarnation where you have the best chance. And what we propose is a simpler incarnation where you have a better chance is to look at the three-dimensional version of this duality, where you look at string theory and AdS3 being dual to a two-dimensional conformal field theory. And you get benefits on both sides. Two-dimensional conformal field theories are under very good control. You have lots of structure, lots of symmetries, lots of techniques. And the other major advantage is that while generically the string backgrounds, AdS string backgrounds don't have a really usable worldsheet description, there is actually a known worldsheet theory that describes string theory in AdS3, and that involves the so-called SL2R Wessel-Witten model. So you have a foothold on both sides of this duality, and you can hope that maybe you have a chance of harvesting the fact that in lower dimension you have better control, together with this idea of the tensionless limit, to make a more concrete proposal or test this idea in more detail. So what's the status of the three-dimensional duality? So there, the dual is not a gauge theory. The dual is believed to be what's called the symmetric orbifold theory. So the concrete proposal is, that has been established already in the, or proposed already in the first paper of Maldacena, and there's lots of evidence that this is true, is that string theory in AdS3 cross S3 cross T4 is dual to the symmetric orbifold of T4, which means you take n copies of T4. So this n will play the rank of the gauge group, the role of the rank of the gauge group, and you divide by the symmetric group in the sense of an orbifold of 2D CFTs. Now, one should be a little bit careful in saying that these two things are dual to one another, because both theories sit on a moduli space of such theories. There is not just one string theory in AdS3 cross S3 cross T4. And conversely, the symmetric orbifold of T4, this is a two-dimensional conformal field theory that has many exactly marginal operators. So you can perturb this theory in many different ways. And there's a whole moduli space of theories that live on the same moduli space as the symmetric orbifold of T4. So the consensus was that if you pick some string theory in AdS3 cross S3 cross T4, it'll be dual to some conformal field theory that lives on the same moduli space as the theory that also contains the symmetric orbifold of T4. So there's a whole 80-dimensional moduli space, and some point here is proportional, is to be identified with one point here, but you don't quite know which point is being to be identified with which point. Now, and in fact, this is what I say on this slide. So while it was, there's very good evidence that this sort of generic statement is true, it wasn't known which precise string background corresponds to the symmetric orbifold theory itself. I mean, there's one preferred theory on this moduli space of 2D CFTs, namely the theory that is the symmetric orbifold theory itself. And it's not known what the precise string background that corresponds to it should be. I mean, what precise string theory in AdS3 cross S3 cross T4 is exactly dual to the symmetric orbifold of T4. And conversely, there is one specific theory we know here. This is this Maldacena-Oguri SL2R Wessel-Witten model. And it wasn't known to which point in this moduli space of 2D CFTs this was meant to be dual to. So you had some moduli spaces. You believed any point here gets mapped to any point here. You had two special points on these moduli spaces, but you didn't know how they were related to one another. And there was only one consensus, which is that the two special points are not related to one another. So this was the sort of overall consensus. And the reason for that is that string theory, this Wessel-Witten model description of string theory, has what are called the long string solutions. So this, so AdS3 has the topology of a solid cylinder. And this Wessel-Witten string background has solutions where the string goes out to infinity, to the boundary of AdS, goes to the middle and comes back out to infinity, these long string solutions. They go arbitrarily close to the boundary, and they are supported at the boundary by the fact that there is the tension trying to shrink it, but the NS-NS flux is pushing it back, and there's a stable solution where the string can sort of live near the boundary. And it's very redshifted there, and as a consequence, the excitation spectrum around that point is a continuum. So you would believe that the Wessel-Witten description has a continuum of low-lying degrees of freedom, and this continuum is not present in the symmetric orbifold theory itself, where there is no sign of any continuum, and therefore it was concluded that these two theories cannot possibly be dual to one another. So that's sort of the state of the art of the AdS CFT duality for the case of AdS3. There are some simplifying features because we have a solvable worldsheet description, we have a good CFT description for the dual CFT, but one didn't quite know exactly how the various pieces would have to fit together. So now our idea was, well, I mean, this is maybe a bit explaining the story backwards. I mean, this is not consciously what we did, but this is sort of how you can tell the story now in retrospect, is to, in some sense, try to put these two ideas together. So the idea is that we want to use insights from the higher spin CFT duality to make progress with identifying the worldsheet description of the symmetric orbifold. So we want to ask which point, what is the precise string background that's dual to the symmetric orbifold theory? And we want to use, and I'll explain in a second why this is useful. We want to use the higher spin CFT duality to help us along the way. So what's the first step? The first step is to generalize this four-dimensional AdS, higher spin AdS CFT duality to 3 dimensions. And this is what we did more or less exactly 10 years ago. We found a specific higher spin theory in AdS3, and we identified the 2-dimensional CFTs to which it is due to, and we provided lots of evidence for this claim. And again, because it's in lower dimensions, you can, in some sense, prove this better than you could prove the Klebanov-Polyakov duality, because it simply has sharper tools. You have better tools to describe higher spin theories in AdS3, and you have sharper tools to construct or to characterize 2-dimensional CFTs. Now, this is a bosonic duality. So in order to make contact to string theory, you want to look at its supersymmetric generalization. And this took us a few years, but there is an n equals to 4 supersymmetric generalization, and the details are not very important, but this is a certain coset CFT that's dual to a supersymmetric higher spin theory in AdS3. So this is the supersymmetric generalization of the Klebanov-Polyakov duality in 1 dimension lower. Now, the key insight that allowed us to make progress was the fact that, you see, this 2-dimensional conformal field theory you have under very, very good control. And what we observed is that if you take the limit where this level parameter goes to infinity, what you find is that this coset theory is actually naturally a subsector of the symmetric orbifold of T4. And what I mean by that is the actual symmetric orbifold theory, not a theory that lives on the same moduli space, but the actual symmetric orbifold theory contains, in some sense, this Wolf space coset theory, which we argue to be dual to a higher spin theory in AdS3. So what this tells you is that the symmetric orbifold of T4 contains some subsector that looks to be exactly like the leading redshift trajectory higher spin description of string theory in the tensionless regime. So what this therefore suggests is that the string theory that's dual to exactly the symmetric orbifold theory should contain a higher spin subsector. If the dual CFT contains this Wolf space coset, what this should mean is that the string theory should contain this higher spin theory subsector coming from the leading redshift trajectory. And as a consequence, what this should mean is that the symmetric orbifold is dual to string theory at a place where you have a higher spin symmetry, but the higher spin symmetry comes when the whole redshift trajectory has become massless. So this arises in the tensionless limit. So what this whole detour about the higher spin CFT duality taught us is that we would expect that the string theory dual to the symmetric orbifold is at the tensionless point, is at a point where the string tension is basically 0. So you've got all of these massless higher spin degrees of freedom whose boundary version is exactly a part of the symmetric orbifold. So the symmetric orbifold contains pieces that are the boundary version of a higher spin theory, and therefore this higher spin theory must be part of the string theory dual of the symmetric orbifold, and therefore the symmetric orbifold, the string theory dual of the symmetric orbifold should sit at the tensionless point. Now the tensionless point, as I explained to you before, is the point that's far away from supergravity. So that's the point where the string size, the string is very floppy, the string is very large, so the string is as large as the space in which it propagates, or put differently, the space is as small as the typical size of the string. So this is the deeply stringy regime where you can't describe string theory in terms of supergravity, where you have to use worldsheet methods to describe string theory. And if you think about it in the context of the Wessel-Witten description, the level of this SL2R affine theory is a measure for the size of the SL2R, of the AdS3 space in string units. So what it suggests is that the symmetric orbifold of T4 should be dual to this worldsheet theory of this Wessel-Witten description at the smallest value for the level, and which we claim to be level being equal to 1. Now, obviously, at this stage, it's not clear that the Wessel-Witten description will have anything to do with the symmetric orbifold, but if it does, then its only chance of having something to do with the symmetric orbifold is in the limit where the level is as small as it's allowed to be, because that's where you would expect the tensionless regime to occur. So this long development, what it really amounts to at the very end of the day is that it encouraged us to have a very careful look at the level 1 SL2R Wessel-Witten model description of string theory in AdS3. In some sense, this is something one could have done 20 years ago, 30 years ago, when Maldaceno and Oguri started this worldsheet description of string theory in AdS3. But people didn't look at it because they didn't think that that was necessarily the right place to look. And what this motivated us is just to have a very careful look at this theory and just analyze systematically the space-time spectrum of this specific worldsheet theory. Now, this worldsheet theory, as it will turn out, is quite complicated, and you have to, I mean, while all the technology in some sense was available, you had to look at it very carefully. But what we found is that once you understand the theory properly, what you realize is that it reproduces exactly the spectrum of the symmetric orbifolds of T4. And what I mean by that is not just the BPS spectrum. So when people compare the AdS CFT duality, they often calculate BPS quantities on one side and compare them to BPS quantities on the other side. But here we have an exactly solvable worldsheet description, and we can just study the entire space-time spectrum of this string theory. And we can compare this entire space-time spectrum, including all the non-BPS states, with all the symmetric orbifold gives you. And what we showed is that the spectrum agrees exactly. You get an exact match between every state in the symmetric orbifold, or to be precise, the single particle states with the single string states from the worldsheet perspective. And more recently, which is what I'm going to explain towards the end of my talk, we've also managed to understand that the correlation functions of the symmetric orbifold are in fact can be reconstructed from the worldsheet perspective. So this is a place where you have a concrete prediction for which two solvable theories are dual to one another. They look totally different. One is a 2D CFT. The other one, incidentally, is also a 2D CFT, but it's the worldsheet of a string, and you don't think of it as a 2D CFT. You think of it as a worldsheet of a string. You calculate the string space-time spectrum associated to it. So it's a very, very different calculation. And that space-time spectrum matches one-to-one with the spectrum of the symmetric orbifold, and the correlation functions also match. So this is a place where you really have a chance to prove the AdS CFT duality, showing that two very different descriptions are in fact exactly equivalent to one another. So this is what I want to, after this somewhat lengthy introduction, this is what I want to explain to you in the rest of the talk. I mean, I try not to be too technical. I want to give you the gist of the argument for how we see this. So the first two chapters will be explaining why the spectrum matches. And then the fourth chapter, I want to explain to you how you see that the correlation functions match. And then I'll conclude. But maybe this is also a good time for questions, and I'll see how much of this I cover if it takes too long.
Yeah,
are there any questions, or is this?
I had one question. I'm just wondering, what would constitute a proof? What are you missing now?
Well, I mean, the fine print. I mean, we haven't proven that all. So what you have to prove is that the spectrum matches and all correlators match. So what we've proven so far is that the spectrum matches and a certain set of correlators.
Oh, a certain set of correlators.
But we haven't yet managed to relate all correlators. But if I have time, as you'll see, the way the correlators match is in such a way that you could hope that there is a manifest way of matching them, and therefore matching all of them. But that is the one point we haven't quite tidied up completely.
I have another question.
Yes.
When you compare basically two moduli spaces,
yes,
then one useful in the conformal field theory side, you probably can calculate the geometry of the moduli space as some Riemannian orbifold.
Yes.
Can you do that on the string side too?
I think the supersymmetry of the string side is also sufficiently restrictive to tie down. I think the global structure of these moduli spaces, I think also agrees. I think that you can. I mean, I'm not sure to which extent this has been totally proven, but certainly I mean, you can look at the tension space, and then I think you can integrate it up. And the supersymmetry, I think, is enough to show you that it's basically of 04, 20 divided by 04 cross 020 divided by some discrete group. So it's this sort of type of moduli space, and I think that's the global structure that's compatible with supersymmetry. So the moduli space, I think, they will match. But what we are aiming for here is not to match the moduli spaces, but to find two specific points, one on each side, that actually match exactly.
Well, normally when you have modded out all isomorphisms, then the moduli spaces have no symmetry anymore. At least that's my experience from the K3 case. And so when you know the location of one point on the moduli space, then you would know exactly which theory corresponds to which one.
Right, but I mean, I think, absolutely, but I think the way people understood the string theory was that they couldn't understand the string theory well enough to locate it where it was on the moduli space. I mean, on the CFT side, obviously you have things under very good control in the 2D CFT side, but the string theory side, and as I'll explain in a second, as I mentioned before, I mean, people didn't think that the Wessel-Witten model had anything to do with the symmetric orbifold. So they didn't even have a worldsheet description for the string. They really only had the supergravity description. They knew the BPS spectrum, but they knew virtually nothing else. So as a consequence, they had no idea where they were in the moduli space.
Thank you.
Okay, if there are no further questions, then maybe I'll explain to you a little bit the sort of the steps in the argument towards proving that. And so the first step is that we want to study the Wessel-Witten model, and there are really two formulations. One is sort of the more standard formulation, and you need to use some sort of slightly more fancy technology. So let me first explain to you what this, how you would normally think about this worldsheet theory. So the worldsheet theory is a Wessel-Witten model based on the Lie algebra SL2R. It's a sort of supersymmetric version, which is what this super index 1 means here. And what this means is you get free fermions and you get an SL2R level K+2 affine algebra that decouples. I mean, they're decoupled from one another. Now, in order to understand this theory, you have to think about what are the, so this is the algebra, and then you have to describe the spectrum. You have to know which representations. And the representations, according to Maldacena and Oguri, are the so-called, so the highest rate representations are either discrete lowest rate representations of this sort of kind, where sort of one of the generators kills the state and you get this sort of semi-infinite lower tail, or continuous representations that are unbounded in both directions and that are simply characterized by the Casimir, as well as a parameter that tells you the quantization modern integer. And the picture you should have is that the discrete lowest rate representations describe the short strings, and so the strings that are sort of near the center of AdS, and the long strings, the strings that wander out to the boundary of AdS, correspond to the continuous representations from this worldsheet perspective. So that's the spectrum. And then there's another complication, which I don't want to get into it in any detail, but there are actually finitely many representations finitely many discrete representations if you look at finite K. And what you need is you have to look at so-called spectrally flowed images of these representations. So a spectral flow is basically an outer automorphism of the affine algebra of SL2R. And if you have a representation and you apply an outer automorphism to it, you get another representation. And the representations you get are these, what are called these spectrally flowed images. They are not conventional highest rate representations, but you can get them under control by virtue of the fact that they are related by this outer automorphism to standard highest rate representations. So that's sort of basically the string spectrum. And then you have to do what you would do if you open any book on string theory. Say you open up Green-Schwarz-Witten. How do you calculate from a worldsheet description the space-time spectrum? We are sort of in covariant quantization. So what you have to do is you have to impose the physical state conditions. And then you look at all the states of your worldsheet conformal field theory that satisfy these two conditions. You have to model out by the spurious states. And this gives you the entire space-time spectrum of this string theory. And what will be important for us is in particular the second condition. And if you rewrite this in terms of the numbers, the Casimir of SL2R will appear from the L0, and then you have some excitation number here, and this a half is equal to this a half. That's sort of the mass shell condition, and that's sort of, as we will see, one of the key ingredients in order to relate this to the symmetric orbifold. So this is the worldsheet description. Now you want to relate this to the space-time picture, and how are you going to organize the states? Well, you know that the space-time symmetry has a Möbius symmetry, and the Möbius generator of the space-time CFT, which is L0, L1, and L-1. These are just a Möbius group on a sphere. They are to be identified with the zero modes of the SL2R Wessel-Witten model. So the SL2R affine Kac-Moody algebra has a finite dimensional SL2R subalgebra, and the generators of this finite dimensional subalgebra are to be identified with the Möbius generators of the dual CFT. So what we are going to do is we are going to take this worldsheet theory, this very explicit worldsheet theory, we are going to run through these steps, and then we are classifying the states we get, and we are labeling them by the conformal dimension they have, which means the J30 eigenvalue on the worldsheet, and that will tell us what's the conformal dimension of the corresponding space-time state that we will see. So here we have a concrete worldsheet description. We can just go ahead with this exercise of working out all the states that satisfy that and classify them according to the L0 quantum number, and thereby know what the spectrum of the dual CFT is. Now we're interested in the tensionless regime. So as I said before, this means we should take the level of this SL2R Wessel-Witten model to be 1. This is the supersymmetric one, so the bosonic one will be at level 3. So this is what we're going to do. And as it will turn out, and I don't have the time to explain this, the interesting bit comes from the spectrally flowed continuous representations. I mean, it's not obvious why this is the right place to look, but if you look at the spectrally flowed continuous representations, this is where we will see the interesting states. And as I'll explain later on, at k equals to 1, these are in fact the only representations that are allowed. So for the spectrally flowed continuous representation, the mesh shell condition, the analog of this mesh shell condition, okay, there's this spectral flow parameter W, which tells you which automorphism you have applied. And then the mesh shell condition takes this simple form. So this is the Casimir of SL2R, which for the continuous representations is a quarter plus p squared. Then you have this W shift coming from the spectral flow. N is still the excitation number, is equal to a half. And M here is the J30 eigenvalue before spectral flow. And now the idea is simply that you take this equation and you solve it for M. I mean, this is an equation which you can evidently solve for M. I mean, there's only one M appearing here. There's one equation, so you can solve it for M. Let's set P equal to 0. So let's sit at the bottom of this continuum for reasons that will become clear. And then you simply solve this equation. I mean, this is very trivial algebra to solve it for M. And then you recall that the actual J30 eigenvalue after the spectral flow gets this additional shift by W over 2. And then if you plug this in, what you see is it has a term that goes like N over W plus W squared minus 1 over 4W. And if you know a little bit about symmetric orbifold CFTs, you will recognize that this is exactly the spectrum of a symmetric orbifold, where in the symmetric orbifold, you have this, you divide out by the symmetric group. The conjugacy classes are labeled by these cycle shapes, and the single particle states, i.e. the ones you should see from a perturbative string analysis, correspond to those where you have a single cycle of length, of arbitrary length, and W is to be identified with the length of the single cycle twisted, W cycle twisted sector of the symmetric orbifold. And if you, I mean, I don't have time to explain this in detail. If you know this a little bit, then you will probably recognize that in the W twisted sector, the mode numbers will be W fractional moded, and you have some ground state energy, and that takes the form W squared minus 1 over 4W. And it just so happens that out of this sort of worldsheet calculation that has nothing to do with symmetric orbifolds, out pops the formula that looks exactly like the symmetric orbifold spectrum. And so this suggests to you that this k equals to 1 theory may have something to do with the symmetric orbifold. And you can actually, you recover the full single particle spectrum. I mean, we only look at single cycle sectors that corresponds to single string states. But because you have arbitrary excitation numbers, you in fact get that's what you would expect the perturbative regime to be, that you take the 1 over n to infinity, and then later on we'll worry about 1 over n corrections. So this is sort of the first hint that this worldsheet theory at k equals to 1, its space-time spectrum looks very, very much like the symmetric orbifold of some theory, but there's a little bit of fine print that makes this a bit tricky. I mean, if you do this honestly, you get some negative level SU2 factor, and I haven't explained to you why I only get the continuous representations. I haven't explained to you why I can throw away the discrete representations. I haven't explained to you why P is equal to 0. So this is sort of the first hint why this may work, but it's not satisfying on the level of a complete description. And in order to get a more complete description, we have to use this other description, which doesn't break down at k equals to 1. The standard Maldacena-Auguri description breaks a little bit down at k equals to 1 because of this SU2 factor appearing at level -1. But there's an alternative way of describing string theory in AdS3 cross S3 cross T4 that involves a supergroup, and that makes perfect sense at k equals to 1. And I want to briefly explain to you what this is. So this is the so-called hybrid formalism pioneered by Berkowitz, Waffer, and Witten in 99. And there, what they argued is that string theory in AdS3 cross S3 cross T4, you can describe in terms, again, of a Wessel-Witten model in terms of the supergroup PSU1,1/2 level K, together with a topologically twisted sigma model for T4. So this is an alternative. This is sort of in this pure spinor way of describing string theory. It's a bit of a hybrid between the Green-Schwarz formulation and the Neveu-Schwarz formulation, Neveu-Schwarz-Ramond formulation. But what Berkowitz, Waffer, and Witten argued is that you can describe string theory on AdS3 cross S3 in terms of this supergroup Wessel-Witten model and a T4. And some years ago, together with one of my PhD students, we actually checked this in some detail. We checked that the spectrum really seems to agree. And I think people do believe that this is just an alternative way of describing the Maldacena-Auguri, Neveu-Schwarz-Ramond-like description that I was using before. Now, what's nice about this description is you see PSU1,1/2, the bosonic subalgebra is SL2R plus SU2. I mean, this is SU11, which is the same as SL2R plus SU2. And these are, in fact, the symmetries of AdS3 cross S3. So the space-time symmetries are somehow more manifest in this description. And then the fermionic generators of this are sort of the space-time supersymmetry generators. So it's like in a Green-Schwarz formulation of string theory where space-time supersymmetry is manifest. Now, what's special about this theory is if you look at level 1 is that it's representation theory. So for any level k, this is believed to give you the Maldacena-Auguri description at any value k. But this theory makes perfect sense at level 1. There's nothing wrong with looking at the PSU1,1/2 Wessel-Witten model at level 1. There's no negative level appearing anywhere. And you can ask, what's the representation theory of this super Lie algebra at this very specific level? And as we shall see, this level is much more restrictive than other values of k. And in particular, that will explain why this continuum disappears. So the one way of understanding this has to do with the fact that the bosonic subalgebra of this, as I said, is SL2 plus SU2. And this level 1 of the super Lie algebra means that both of them are at level 1. Now, again, I don't know how much you know about 2D CFTs, but the level 1 SU2 Wessel-Witten model has a very restrictive representation theory because it only allows for two representations, and it is the one-dimensional and the two-dimensional representations. So spin equal to 0 and spin equal to 1/2 are the only ground state representations that SU2 at level 1 is compatible with. Now, if you look at this, a generic representation of the super Lie algebra, and you look at the zero-mode algebra of it, then it's a typical long representation takes this form, where the first entry here is always a continuous representation of SL2R. So it's labeled by the spin and this parameter alpha that tells you the quantization mode integer. And n is the dimension of the SU2 representation. So the number I give here is the dimension. So 1 means the one-dimensional spin 0 representation, and 2 means the two-dimensional spin 1/2 representation. Now, if you look at a generic long representation, because you have 8 fermionic zero modes, you get this 16-dimensional space of representations that you go along with this super algebra, with these fermionic super generators. And what you spot is that you see there's always, if you start with a representation of dimension n, you'll always find a representation with dimension n plus 2 somewhere in this long multiplet. That simply follows from the representation theory of these fermionic zero modes. But on the other hand, I told you that SU2 at level 1 only has 2 possible representations, namely 1 and 2. So even if you start with 1 here, you're going to get 3 here, and that's incompatible with the representation theory of SU2 level 1. So what this tells you is that at level 1, this PSU1,1/2 affine Kac-Moody algebra only allows for short representations. Long representations are incompatible with the structure of the affine super Lie algebra. And in fact, the only representations that are allowed are these short representations where you have 3 summons, one with a one-dimensional representation of SU2, one with a two with a one-dimensional, one with a two-dimensional representation. And if you study for which values of J this shortening can happen, you realize it only happens for J equals to 1/2. So the only representation that is compatible at level 1 is an allowed highest weight representation, is this representation where J takes the value equal to 1/2. But remember the continuous representation, that is continuous parameter describing the long strings. But what this means is the long string continuum has disappeared at k equals to 1 because it's incompatible with the representation theory of the super Lie algebra. So this is remember, the reason why people said the symmetric orbifold can't be dual to the Wessel-Wiener-Witten background is that there's this continuum of which there is no sign on the symmetric orbifold. But at level 1, the continuum disappears for a representation theoretic reason, and there is no continuum, so it has a chance to be dual to the symmetric orbifold. The old no-go theorem has disappeared because the continuum disappears at level 1, and only at level 1. This is very specific to this very small radius setup. So in fact, as it turns out, there are zillions of null vectors of PSU1,1/2 at level 1. The way you should think about it is like SU2 at level 1. SU2 at level 1 is equivalent to 1 free boson. So normally you would have thought it has sort of 3 degrees of freedom because SU2 is a 3-dimensional Lie algebra. But at level 1, the theory is much, much smaller and it becomes effectively 1-dimensional. And PSU1,1/2 at level 1 effectively only has 2 bosonic degrees of freedom in the same sense as SU2 level 1 has only a single bosonic degrees of freedom. And as a consequence, it's that there are far, far fewer states in the representations for this very small level PSU1,1/2 super Lie algebra. And as it turns out, so one can study this. This was studied before also by other people. Once you've removed the ghosts, once you impose the physical state condition, what you find is that none of the degrees of freedom, none of the excitation modes from AdS3 × S3 survive. And the only excitation modes that you are left over with are those from T4. So this comes from the fact that that this is a very special level where you have far fewer descendants, together with the fact that upon imposing the physical state condition, you remove exactly as many descendants as this super Lie algebra has as bosonic descendants. So then you just impose the mass shell condition. Out of this ground state, the 0 mode sum, you pick out one term because M is again picked up by the mass shell condition. And then you get exactly as many states as the symmetric orbifold of T4 suggests. And also there's only one representation because we just studied the representation theory in general, and we saw that that's the only representation that's allowed. That's the only short representation that only happens at J equals to 1/2. So the rest of the analysis works essentially as in the Neveu-Schwarz-Ramond formalism. The continuum has disappeared. There are no discrete representations, and you get exactly the single particle spectrum of the symmetric orbifold of T4, whereas before the spectral flow parameter is the length of the single cyclotwisted sector. So in this case, we really have a very clean way of describing this worldsheet theory because it's this very specific super Lie algebra that comes to play at this small, and its representation theory at this small level, at level 1, is very restrictive, and the space-time spectrum is much, much smaller, and it doesn't have 8 directions worth of oscillators, only 4 directions worth of oscillators, and it matches exactly with the symmetric orbifold of T4. So this is and this I think is essentially rigorous. I mean, I think you may doubt whether Berkowitz-Vafa-Witten really describes strings on AdS3 × S3 × T4, but I think this worldsheet theory, its spectrum is exactly the same as the symmetric orbifold of T4. I mean, single particle states of the symmetric orbifold of T4. So this is what I meant by saying that we've shown that the spectrum matches, and that matches the entire spectrum of the symmetric orbifold with all the physical states you get from the worldsheet description. Now, in order to prove the two theories are the same, you have to show that the spectrum is the same, and you have to show that the correlation functions are the same. So what our more recent work is concerned about is showing that the correlation functions are the same. So I don't have that much time left, so I'm just going to sketch a little bit of how this argument works. And it actually is a very nice geometric argument that underlies it. And I want to at least give you the gist of the flavor. So the symmetric orbifold, there's a very neat way in which you can calculate correlation functions of twist fields in the symmetric orbifold. And the idea is that you can think of it in terms of covering maps. So I haven't really explained to you what these twist fields are, but these twist fields are basically, remember, you have n copies in the symmetric orbifold, and around the twist field, you're basically permuting these copies. So as you go around, you cycle through W copies before you come back. So a twist field locally looks like, if you sort of unfold it, like something that has corresponds to a twisted map. It corresponds to a map where you map z to x plus the wth power of z goes to a constant plus some constant times z minus z0 to the w. So it's a w-fold spiral case on top of the point. And the correlation function of the twist fields in the symmetric orbifold you can describe in terms of covering maps that locally look like w-fold coverings of that kind. Now, if you want to calculate a real correlator, what you will have, you have, say, different twist fields on the sphere, and around each such point, you have a twist field of twist w. So you think of locally covering it by a w-fold cover at that point. And then you want to do is you want to glue these different local coverings together into a global covering surface. So you have different points on the sphere. Over each of these points, you have some picture that looks roughly like that, where if you go around once here, you go from sheet to sheet to sheet. And now you want to put these local descriptions together in a global way, such that the sheets sort of link up between the different twist fields that make up your correlator. And the global map that achieves that for you is what you call the covering map. It's an analytic map from some Riemann surface down to the surface, to the sphere. In our case, we are interested in calculating these correlators on the sphere, such that near each of these insertion points, the covering surface looks like a W-fold cover around that point. So that's what the covering surface is. Now, you asked me before, in which sense haven't we proven it? Well, we've really only looked at the twisted sector ground states at the moment. So we haven't looked at correlators of arbitrary states, but we've looked at the correlators of twisted sector ground states. And the twisted sector ground states, for them, life is very simple, because what you can do is, suppose you have a twisted sector ground state, then you replace this description by a conformal map, and this is a conformal field theory. So you can, upon applying a conformal map, you describe the same theory on some other surface. You go to the covering surface. But once you've gone to the covering surface, the twist field has disappeared. The twist field has been absorbed into going to the covering surface. The only role the twist field had in life was to make this twist. So once you've got into the covering surface, nothing is left at the position where the twist field's at. So what you get is you get the vacuum correlator on the covering surface is the same as the correlator of the twisted sector ground states on the original sphere. But the vacuum correlator is just a number. So everything is just determined by the conformal map that maps the original surface to the covering surface, i.e. the covering map. So the entire correlator is just determined by the conformal factor that comes from the analytic map that maps your original surface on which you're calculating the correlator, say the sphere, to the covering surface. So the correlator, that's one way of calculating the correlation function in the symmetric orbifold. That was pioneered by Lunin and Matthias, and that's a very clever way of calculating it's a very good idea to do it. And as we will see, that's the way that makes very direct contact with what we are seeing from our string theory worldsheet description. Now, in order to understand or to guess why that may be so, it's important to realize that if you start with a sphere and you have some twist field insertion and you go to the covering map, I mean, locally everything is simple, but once you start linking these things together, you're going to end up with a covering surface that's not necessarily topologically a sphere. You're going to end up with a Riemann surface, and it will have a genus. And the genus may be whatever it may be. There is no guarantee. It depends on the assignment of the covering points and on the choice of your covering surface. But in general, there will be a non-trivial genus coming from this covering surface that sort of links together this local structure will in general have a non-trivial genus. And what Lunin, Matthias, and also Pachmann and Restelli and Razamet observed was that if you calculate the correlators of the symmetric orbifold and you systematically ask how they scale with n. N is the number of copies in your symmetric orbifold. Then they scale with n in terms of the genus of the covering surface. So the genus of the covering surface appears naturally in describing the large n behavior of the correlators of the symmetric product CFT. Now, if you think a little bit about how this should fit together with string theory, you know that n, the rank of this symmetric orbifold, is to be related to the string coupling constant on the string theory side. And in string theory, the contribution related to the string coupling constant will go like the genus. So therefore, what it suggests to you, the genus of the worldsheet that you have to calculate in order to calculate that contribution. So what that suggests to you is that you should think of the covering surface, that is some abstract concept that you calculate, that you introduce in order to find a smooth way or a simple way of calculating these twisted sector correlators. You should think of as being the worldsheet, because its genus appears exactly at that place where the genus of the corresponding worldsheet should appear. Namely, it controls the 1 over n expansion of these correlators exactly as you would expect the genus of the worldsheet to control it. So what Pachmann, Rastelli, and Razamad already proposed is that the worldsheet should play the role, the worldsheet of the putative string theory dual. They had no idea what string theory that would be. They didn't know how to write down a concrete model. But what they suggested is that whatever string theory is dual to the symmetric orbifold, its worldsheet should play the role of the covering surface that appears in the calculation of the correlators when you calculate the twisted sector correlators of the symmetric orbifold. But now we have a concrete prediction for what this worldsheet theory is, so we can simply go ahead and check this idea. We can check whether the correlators that we calculate from the worldsheet behave as though the worldsheet is the covering surface. In particular, there is then a covering map, and the covering map via the Liouville term will determine the value of the correlator, and we can simply check whether the correlators that we can calculate on the worldsheet have this property or not. Because I mean, this is a concrete solvable worldsheet theory, and we can simply study its correlation functions. We know which state corresponds to which state. We know which state on the worldsheet corresponds to the twisted sector ground state. So we can analyze these correlators and see whether this picture comes out right. So these correlators are labeled by spectral flow that corresponds to the twist along this and the branching of the covering surface. Then you have a worldsheet coordinate over which you will have to integrate, because in string theory you have to integrate over the worldsheet coordinates. And there's a parameter that will play the role of the CFT coordinate of the dual CFT. And then there is a parameter that labels the conformal dimension of the space-time field. Now, I don't have the time, and it's quite a complicated calculation, but there's one very easily understandable fact that one can spot almost instantly. You see, so the symmetric orbifold perspective suggests you should be able to calculate in terms of a covering map, but covering maps are not that easy to find. I mean, there's a whole Hurwitz theory to explain to you why covering maps exist. In particular, if you fix the coordinates on the covering surface, you fix the coordinates on the downstairs surface, and you fix the covering, the branching number, then generically a covering map will not exist. And the easiest way of understanding this is think of the 4-point function where all w's are equal to 1. Then the covering surface is just another sphere. The covering surface of the sphere is just a sphere. And in fact, the map must locally be 1-to-1, so it must just be a Möbius transformation. But a Möbius transformation maps 3 points to 3 points, and then the 4th point is fixed to go to the 4th point. So this covering surface will only exist provided that the cross ratios of the x's agrees with the cross ratios of the z's. So if I specify all the x's, I specify all the z's, I specify all the w's, say in this case w equal to 1, the covering map only exists provided that this one condition is satisfied. If this condition is not satisfied, there is no covering map. So what that suggests is therefore that these correlators must be 0 unless they line up in such a way that the covering map exists, that the zi's conspire to be such that they are compatible with the xi's and the wi's, i.e. for the case of the 4-point function, that the two cross ratios agree. Now this is a long, complicated paper. What we did is we took this correlator, we studied in principle something people could have studied, ward identities, but ward identities are quite complicated because these are spectrally flowed vertex operators, so it's not entirely trivial, but we managed to find ways of constraining these correlators via ward identities. The equations are quite complicated, and we haven't managed to solve them completely. But what's totally striking is that the ansatz that produces the Lunin-Matur answer, and that involves delta functions for the relevant cross ratios, solves all of these complicated ward identity relations, provided that k is equal to 1 and all the j's are equals to 1/2. So this is a seemingly magic way in which this comes out, that these correlators are at least compatible with this Lunin-Matur answer, and they show this delta function behavior, which is very unusual for a CFT, but which in some sense is required in order for this whole AdS CFT correspondence to work. And you see, because of this, I mean, if this is indeed the correct solution to the ward identity equations, what this in particular means is that this worldsheet integral that you have to do in string theory, where you have to integrate over all the variables z, what will actually happen is that there are delta functions, and this worldsheet integral will localize to a finite sum, namely to those configurations that allow a covering surface. And then, so the worldsheet integral will actually become a finite sum, and the theory will just reproduce the different contributions from the covering map as you would calculate them in Lunin and Matur. And it also suggests that this sector behaves a little bit like a topological theory, and this sort of has repercussions with ideas that Berkowitz already put forward many years ago, that string theory, the AdS CFT correspondence in the tensionless regime should behave a little bit like a topological theory. But here we see this sort of very hands-on, we see very concrete evidence that many of these ideas that people have sort of put forward are actually very concretely realized in this specific example. So I think I'm running out of time, or maybe out of time. So let me conclude. We've given strong evidence that a symmetric orbifold is exactly dual to string theory with one unit of Neveu-Schwarz-Neveu-Schwarz-like, this k equals to 1 theory. The spectrum agrees precisely, and the structure of the symmetric orbifold correlators is at least reproduced on the level at which we've understood so far from the worldsheet. The worldsheet plays the role of the covering surface of the symmetric orbifold, and this suggests that somehow you can maybe turn this in a more systematic way of rewriting it, instead of sort of checking these ward identities, really showing that you can rewrite it in this way. And among other things, it suggests that this will not just work at leading order in n goes to infinity, but it will reproduce correctly all 1/n corrections, because they will correspond to the covering surfaces that higher genus, and they will exactly come from higher genus worldsheets. And recently, my former student has checked that this magic localization property also works if the worldsheet is of higher genus. So this really seems to suggest that this duality, you can make it in some sense manifest, and you cannot just prove it in the n goes to infinity limit, the planar limit, but this is the analog of proving it to all non-planar degrees of freedom, to all orders in 1/n. The worldsheet theory exhibits signs of a topological theory, and this is something that fits together with what other people have observed over the years. Both sides are explicitly solvable. In fact, there is a free field realization of this PSU 1,1/2 Wessel-Minowitten model. And what we are currently doing is using this free field realization to prove that the correlators have in this form. And we are more or less there in proving that. So this is what we are currently trying to do. We are trying to prove that this worldsheet correlator that is expressed in terms of the covering surface is in fact the only solution to the ward identities, and using the free field realization, which we've learned to get under control, we are very, very close to proving that. I mean, on the sphere, I think we've essentially proven it. And then this hint that it's a topological string theory suggests that you should be able to write this worldsheet theory in a way that looks like a topological string theory. And this is what I'm currently working on together with Rajesh. And so we are not quite there yet, but I think it looks promising. So these other things are together with my current PhD students and partially Rajesh. So Andrea Day is a finishing PhD student, is going to go to Harvard, and Bob Knighton is a new PhD student. Then one could ask whether one can also understand this more directly in the NSR formalism, but obviously the holy grail would be to use similar ideas to try to use this for AdS5. And now this is obviously a bit of a bold statement, but you may think that there is also something like a free field realization corresponding to Super-Yang-Mills at a free point. I mean, our picture is that the free Super-Yang-Mills theory, the special features of it are have their counterpart in the fact that the worldsheet theory at that point is also a free theory. We see this here, and we believe that this may very well generalize to AdS5, and that there'll be some similar free field description for some string theory describing AdS5 process 5, namely PSU 2,2/4, which basically looks like 2 copies of PSU 1,1/2. But this is obviously science fiction. But I think we have what our mission, what our vision is that what we managed to get under complete control here, we feel has a fair chance to also generalize to higher dimensions. Okay, so with this I stop. Thank you very much.
Thank you very much for a stimulating talk, Matthias. And the floor is open to questions.
Matthias, what do you know about the partition functions for the covering spaces? So, for example, when you have genus 1, then you should get some modular function. Have you calculated that?
I mean, we know the spectrum. I mean, we know the space-time spectrum in the world. So the genus 1 case we sort of know, right? Because that's just the partition function of the symmetric orbifold. I mean that's. I mean, you mean calculating the
yes.
partition function of the dual CFT. So that's just the standard. I mean, digraph, Verlinde formula for. So
you reproduce that, but as far as I know, not too much is known, even for genus 2.
True. So genus 2, we haven't tried to calculate the higher genus amplitudes. What we've done is we've matched the spectrum, which in some sense is matching the genus 1 answer. And we've been thinking about calculating correlators on higher genus. We've not been trying to calculate the vacuum amplitude on higher genus. But that's obviously an interesting question. But that's bound to be hard. I mean, as you know, higher genus amplitudes are bound to be hard because they have all these moduli and it's complicated. You would expect here it to be easier because it somehow gets localized, but it's probably still a hard problem. It's a good problem, but I haven't thought about it.
Okay.
May I ask a question?
Please.
Sure.
So I want to know about this topological string theory picture that, well, usually we know that if the target space is not like, well, something very special like a Calabi-Yau, there will be like anomaly.
Right, so this is not quite a standard, I mean, it's not a topological string, right? Because the full spectrum is the entire spectrum of the symmetric orbifold. So this is not, but a piece of it, the AdS3 process 3 piece, behaves in some sense like a topological theory. So what we have in mind here is that what we're in the process of doing is rewriting our worldsheet theory as a critical n equals to 2 string theory. So we want to reformulate the physical state condition in this hybrid formalism in this free field theory as you would do if you were to calculate critical n equals to 2 string theory. Now, critical n equals to 2 string theories are typically topological string theories. These are not what people normally look at, but here what happens is if you look at U1,1/2 plus T4, because U1,1/2 has conformal dimension 0, T4 has the conformal dimension 6, so you're sitting exactly at C equals to 6, which is the critical value for the n equals to 2 critical string theory, and it looks very much as though that you can describe alternatively the full space-time spectrum as the topological string spectrum of this n equals to 2 worldsheet theory. And that will probably, as a side product, allow you to show some of these localization properties using n equals to 2 critical string theory techniques. But it's not a topological string theory in its entirety. But the way we want to describe it is as a critical n equals to 2 string theory from the point of view of the worldsheet.
So
this is not, say again?
Do you expect it to have some relation with like Chern-Simons theory?
What Chern-Simons theory do you have in mind?
Well, because well, for usual topological string theory, I think Witten had a paper about the duality with Chern-Simons theory in 3 dimensions.
Yeah, I don't think this theory directly will be equivalent to a Chern-Simons theory. I mean, there's a Chern-Simons description for this higher spin theory, so pieces of it have some Chern-Simons formulation, but I don't think the whole thing will be equivalent to a Chern-Simons theory. But it's, I mean, it's topological. I mean, maybe I should have put this in quotation marks. It's topological in a very specific sense, but in the sense that it has to reproduce these funny properties. I mean, these properties, these delta function localization properties, the fact that the spectrum only has short representations of p is 1,1/2. These are sort of smell like some sort of topological theory. So, I mean, we're not saying it's a standard topological theory, but it has aspects of it, and a way to make some of these aspects manifest is to write it in terms of a critical n equals to 2 worldsheet theory.
Okay. Okay, thank you very much.
Charles?
I was wondering, do you have anything to say about non-free field realizations?
Yeah, so I mean, the ideology here is that, so you're trying to establish AdS5 cross S5, and obviously the free field point is not the world's most interesting point. I mean, you want to understand this theory for the non-free point.
Sure.
But the idea is that, I mean, you have a moduli space of these theories, and if you can show that at one point they agree exactly, then they will also agree if you perturb them on both sides, because perturbing them on both sides will do, if they really, really agree, will do exactly the same thing on both sides. So the strategy towards proving the AdS CFT correspondence for the whole moduli space is to establish it at one point. And the one point where you have the best chance of establishing it is the free point.
Sure,
But,
I understand, yeah.
But the idea is that then you can perturb it on both sides and match and have control over the perturbation on both sides. So an interesting problem is to look at perturbations of this. So that's something that would be very interesting to study. For example, it would be interesting to study what happens when you go away from the point of pure Navier-Schwarz flux. If you switch on Ramond background, that should correspond to a certain deformation of this worldsheet theory, and you can use conformal perturbation theory on the worldsheet, and that should match to conformal perturbation theory or some version of it in the dual CFT.
Yeah, so I mean, a more pressing way of putting what I'm asking is that sort of perturbation within range of these techniques, or do you suspect that you'll need to acquire some more technology?
I mean, to do the perturbation at finite coupling is probably a little bit out of reach. I mean, this I think is very, very hard. I mean, what we are trying to do here is to establish the duality. And I think for that, in some sense, it's enough to prove it at one point. But I agree with you that you would later like to also understand it at other points, but that will require more technology. I think with current techniques, that's probably out of reach. I mean, as Werner probably knows, I mean, K3, there is, on K3, controlling things across the whole K3 moduli space is very hard. And here it'll be at least as hard. So controlling these quantities away from specific points is typically very hard, and this will not be different here.
Okay, thank you for a very nice seminar.
Thank you.
I have a very elementary question, which just shows my ignorance about string theory. On the conformal side, you know the perturbations are by 1,1 fields, 1,1 fields. But what is conceptually the corresponding thing on the string side?
Well, so in the you know so you're interested in the perturbations that preserve the super conformal symmetry.
Yes.
So they have to be chiral primaries. So from the point of view of the, I mean, they have to be, so in certainly the n equals to 2 setting, they will have the fields of h equals to 1/2 that are chiral primaries, and these are the fields that will preserve the, I mean, the worldsheet theory always has an n equals to 2 symmetry, right? Because space-time supersymmetry requires that the worldsheet theory, while you only gauge the n equals to 1 supersymmetry, the worldsheet theory is always n equals to 2 superconformal. And then the chiral primaries of the worldsheet theory describe the moduli that correspond to the space-time moduli. So these are the fields with which you can perturb the worldsheet theory, and there are G descendants of chiral primaries, and that guarantees that you preserve n equals to 2 superconformal symmetry.
Okay.
Do you know what are the deck transformation groups of your coverings?
So again, which groups?
The deck transformation groups. So you mentioned this kind of that Hurwitz theory can be complicated enough. So like when you when you look at the coverings, right, that you do have like this, I think it's called Dex transformation groups. Maybe you use some other terminology. So do you know how they look like?
Not very specifically. I mean, ultimately this will almost certainly play a role. At the moment, our approach has been somewhat more algebraic. I mean, what we've done is, I mean, I've hidden this, but what we've done is we looked at these correlators and wrote down identities and showed that these identities lead to solutions that are compatible, in particular with these delta function properties. And for that, we don't actually need to know that much about the covering surface or its geometry. We just need to know that it's holomorphic. I mean, it's a conformal map. And
no, it's just out of curiosity, right? So it can play a role kind of later, maybe.
It'll probably play a role later. I think it'll play a role. So there is this work of Pachman, Rastelli et al. They try to derive some sort of Feynman rule. So I mean, this symmetric orbifold is a theory that you treat very differently than super Yang-Mills. But if you want to couch it in a language that looks more like super Yang-Mills, you want to develop something that looks like Feynman rules. And what Pachman, Rastelli et al. Did was develop some sort of Feynman rules for that theory, and that involved choosing different covering surfaces, and then obviously there's some redundancy in some symmetry factors, and I think that has to do with sort of the permutation groups that we label.
Yeah, because it can be quite complicated because yes. It's known that almost every group can be realized as a kind of this.
Yeah, so I mean, this is very complicated, but so sort of locally, you can sort of have this under control, and then they put together some sort of Feynman description. It also suggests that it's sort of the covering space description is really the smart way of calculating the symmetric orbifold correlators, and that suggests that they really want to be related to some worldsheet description, with the worldsheet playing the role of this covering surface.
Very good. Thank you very much. Very interesting talk.
Thank you.
So, Matthias, if I might ask, the duality here holds for all n?
Well, so, not really. So, I mean, I should have probably said this more clearly. So what we have in mind here is that you take n to infinity. So why do we have to take n to infinity? So you see the map, the relation between this, where do I have this? Sorry, I have to go back to some slides. The relation is that the cycle of length W gets related to the W spectrally flowed sector on the worldsheet. Now on the worldsheet, there is no limit on how much spectral flow you can apply. So W runs over all positive integers. And therefore, in the symmetric orbifold, you need to have, so W is, so what's the role of W in the symmetric orbifold? So the symmetric group has conjugacy classes, right? Conjugacy classes are labeled by cycle shapes, and the single particle states that you hope to get from a single worldsheet will be the single cycle permutations. So single cycle permutations are permutations of length W, it's just the permutation 1, 2, 3 up to W, up to conjugation. Now, if you work at finite n, then obviously at finite n, you can have at most cycles of length n, because I mean, right? I mean, that's where your world ends. So the worldsheet doesn't see any bound on the length of W, on the value of W. So the worldsheet gives you the spectrum in the n goes to infinity limit. But this is what you should expect to see, because you see the worldsheet is basically a perturbative string theory description. So you should be at weak string coupling, and that means having taken n to infinity. So this duality is meant to hold as follows. You have first to take n to infinity, so you can match the spectrum. But then you can systematically analyze what are the 1 over n corrections to the various quantities that you can calculate. For example, what are the 1 over n corrections to the spectrum? Now, the 1 over n corrections to the spectrum come from the 1 over n corrections to the 2-point function, because the 2-point function is basically a way of calculating the spectrum. And what we've shown is that the 2-point function, well, also, you know, I mean, the 2-point function, the covering surface of two twist fields, is just a sphere. There are no higher genus covering surfaces so what this tells you is that from a string theory point of view, you're not going to get any higher genus corrections to it, which means that the spectrum must be exact. There are no 1 over n corrections to it. But the 3-point functions, the 4-point functions, the 5-point functions, they will get 1 over n corrections, and they will get 1 over n corrections that are labeled by the genus of the covering surface, which you should interpret as being the genus of the worldsheet. So what we claim, or what we believe, is that this works taking n to infinity, but it reproduces correctly all 1/n corrections. Now, this is a strictly weaker statement than saying that it works at finite n, right? I mean, finite n and saying you take n to infinity, but you include all 1/n corrections are very two different statements. I mean, one would be sort of non-perturbative. This is like the perturbative statement. So this works perturbatively to all orders in 1/n, but the finite n truncations, it will not reproduce. But this is what you would expect because we are doing a perturbative worldsheet description of string theory. So in some sense, we are in the perturbative regime. We should not see non-perturbative effects, which would be the finite n effects from the point of view of the symmetric orbifold.
Well, but what you can do is when you think about a 1/n expansion, then it probably will be an asymptotic expansion. And then one should be able to get something like incident contributions in the Borel plane.
True, true, true. I mean,
so
if you can sum it all up, then you may see also some signs of where the finite n effect should come in. But on the level at which we have checked things so far, we really take n to infinity and reproduce all 1/n corrections.
But you believe that the duality holds non-perturbatively, or are you suspicious that it doesn't?
No. We are thrilled that it works on that level. I mean, if you compare to what people have checked for AdS5 crosses 5, there people can check the planar limit. I mean, the 1/n corrections is like all the non-planar corrections to super angles. So this works miraculously, and I don't see any reason why it shouldn't work non-perturbatively, but you may have to understand exactly what the correct non-perturbative completion is and so on. But I don't see any sign that this will go wrong at finite n, but with the techniques that we've used so far, we can only approach the large n behavior and control 1/n correction so far.
Okay, very good, thank you. Any other questions?
Yes, I'd like to ask whether there are some simpler, even simpler models that where one can control this duality. I think Juan mentioned to me something like AdS2 cross S2. Is that much better understood?
Not as far as I know. I don't think anybody has done any analysis on that sort of level of detail for AdS2 cross S2. I mean, I think this is the first example where people managed to get the worldsheet theory under control and managed to match the results from it to the dual CFT. Now, for AdS2 cross S2, there may be other techniques, but not an honest string theory worldsheet description as far as I'm aware.
Thank you very much. Beautiful talk.
Thank you.
If there are no other questions, let's thank Matthias again. Thank you, Matthias.
Thank you.
It's a rather silent forum, but
yeah, that's I'm used to this. I've been on the other side of these things before, so I know how this works.
So I'm going to stop recording at this point, and we can continue a more casual discussion as you wish.
Thank you.
So will the slides be available too?
Yes, we will ask him for the slides. Yes.
Sure, I can